Okay, what we're going to do this morning, or this afternoon, I should say, first of all, we're going to start off with a demonstration of some wave phenomena that I wanted to do last week, but I forgot. And that's the phenomenon called beats. And you've read about it in chapter 11, or I should say chapter 16. And what I've got here, and I'm recording this into the YouTube, so hopefully if you're within the sound of my voice and YouTube, you'll be able to, you won't see this, but you'll hear it. And what I've got here is a couple identical tuning forks made of aluminum, and they're mounted on these wooden boxes, and one end is open so that the sound will propagate out, out the open end. Okay, and the other end is closed, and that'll help conduct the energy, the wave energy outward. Now, they're both the same tone, so let's double check that. Okay, listen. Okay, now memorize that. Here's the second one. Here's the other one. What do you think? Pretty close? Let's just verify again. All right, now. Who's doing that? Don't do it while I'm doing this demonstration. It's cool that you're doing it, but not during the demonstration. Okay, so what we're going to do, these two tuning forks, when I hit both of them at the same time, you'll hear basically double amplitude of whatever frequency they're putting out. And the frequency is pretty close to the same, so you hear the same pitch. So, pretty good. Nice and clear. All right, now, I'm going to place a small metal clip on the end of one of the tines of the tuning fork. I'll put it up here. And what this will do, it will modify the frequency of the tuning fork. Okay, now, if I put this clip up here, what do you think is going to happen to the pitch? Is it going to go up? Is it going to be a higher pitch or a lower pitch? Lower pitch, you think? What about higher? I mean, it's a little more mass, so I mean, well, let's find out. All right, so here's the original, unperturbed. All right. Here's the modified one. It's lower, definitely lower. Okay. Now, here's where beats come in. We've got two sources slightly. You can sit down wherever you want. No, go ahead. Make yourself at home. It's, two different sources, so they'll propagate to your eardrum independently. All right. But when they get to the eardrum, they're going to have a certain effect, and you'll see it. You won't see it. You'll hear it in just a second. So here we go. I'll hit them both, one right after the other. Okay, so you clean out the earwax, and let's see what we can see. Let's do that again. Hear anything? Let's change the position of this. Let's try it now. Hear that? That's beats. Let's try it again. We'll change position just to see, for safety, to see if that changes anything. Now hush, everybody. Shh. Have a seat. We're doing an experiment up here. I just told everybody to hush. Okay. Sounds kind of like a monster movie, you know, when the mad scientist comes into his lab, you know, starts turning on all the equipment. All right, now let's bring this a little bit further down. Let's see what this effect is. All right, that's about a third of the way down, 40% of the way. So that's his enemy. The mad scientist's enemy comes into the lab, hypnotizes the mad scientist. Okay, so that's beats. Now let me bring this all the way down. All right. Now this, we might not hear beats. It might be such a low frequency. You know, if we had a really precise microphone and have you guys used oscilloscopes in the lab upstairs? Oscilloscope will take any kind of an electrical signal, you know, like from a speaker, and put it on a little TV screen, and you'll see the waves go up and down. You see the waveform of this thing, basically the energy or the amplitude of the wave. All right, now there's one more thing I want to show you. Have you ever seen that famous video of the bridge out in Washington State, the Tacoma Narrows Bridge, Galloping Gertie? Back in, I think, 1940 or 41, there was a storm that blew at just the right speed, in just the right direction, just the right barometric pressure and density of the air to cause that bridge to resonate. And it got into what we call standing wave state, and it was not able to, it just kept getting bigger and bigger. And I'll put a YouTube into web courses for a link to it. But it eventually collapsed. It exploded the bridge. I mean, it's, you know, there's a guy out in a car. So it's kind of cool to have films of it. And some guy in a car, it was bad. He bailed out of his car and he ran to the end of the bridge and he left his dog in the car. So then some guy went out to rescue the dog and he rescued the dog. Good. That was pretty cruel. Of course, if that was me, I would have, you know. Now, what I'm going to do with this, these are back to the normal tone. Okay? So we're back to the even Steven. And what I'm going to do is I'm going to hit this one, and I'm going to keep my hand on this one. So I'm not going to hit this one. And this is really subtle, so I want you to listen carefully. So clean out the earwax one more time. Hear that? That's the one I didn't hit. Let's try it again. I'll do this one first, and I'll hold this one. All right. Now, you know what that is? That's resonance. This one over here, the one that I had still to start with, picked up energy off of the other one at just the right frequency, okay, to excite this one. Now, it wasn't real loud because, you know, this one wasn't putting up and out enough sound energy. But that one bridge, yep, exactly, the pressure, temperature, density of the air, the wind speed, the wind velocity, perfect. And the bridge was famous for doing that. And you know, people could feel their cars, you know, the bridge rolling as they drove across. But that day, it went into hyperdrive and it broke the bridge, collapsed into the Tacoma Narrows. Question? Yeah, it was the right size wind. You know, if it had been a little stronger than that, it would have done it. It has to be the right amount of uh, it has to be the right amount of delta P delta T over delta T to excite. Otherwise it's going to pass right on through. It won't excite it. It's got to be just the right frequency, and then bang, you'll get it. So this is resonance. This second demonstration is called resonance. All right, let's go back to the regular part of the lecture. Let me turn the lights off down here. And some of the homework that I told you a couple lectures ago that I like from chapter, I don't know, 11 or, no, chapter 16. One of them is about beats, and it's fairly simple calculation to do. By the way, I did a talking PDF for all three of those problems, and I'll be putting them up on web courses tonight. So you'll see that stuff. Now, any questions about the beat demonstration before we continue? Yes. The question is, what was it about the mass, the little clip? It basically just changed the mass of one time. So F equals ma, right? This thing oscillates because of an F, some kind of an F. I bang on it. I use that the little hammer type deal, and I deposit some momentum in a certain amount of time, and that shocks it. So a little bit of F equals ma. Change the mass, change the A. Change the A, change the, how fast it's oscillating back and forth. It's pretty complex to figure it out. You could do it, but it would require calculus out the wazoo and a whole lot of fancy calculus. So the calculus that those of you that have had even 2 semesters would not be able to hack, but you could do it. In other words, you could figure out, okay, if I put so many grams of mass at such and such a distance from the top, what is my new frequency going to be? You could figure it out. But it'd be pretty bodacious. It's easier just to measure it. So another question. By the way, I think I mentioned this a few times ago. The way that the police catch someone, I know all of you in here are very good citizens and never speed, but you have heard that people get tickets for speeding. And what they do is the police officer beams out a beam of gigahertz frequency rate. It's a radar frequency somewhere in the gigahertz range, and it bounces off your car. Now, if your car's parked, it'll come back at exactly the same frequency. If your car is moving away, it'll come back at a slightly lower frequency, and he'll electromagnetically observe beats. The radar gun will. And from the beat frequency, you can figure out how fast the car is moving away. Same thing if the car is moving toward you. If a car is moving toward the police officer, he'll get a slightly higher frequency than what he sent out, and he'll still get beats. And you could figure out the velocity of the car, whether it's speeding or whether it's in the right zone from the beat frequency. So beat frequency is something important. Every electronic device that you have utilizes beat frequencies in some way. Every electronic, especially if you're listening to anything, any kind of music, you've got heavy digital filtering and stuff, and all that's related to oscillations and beats. Beats will help you filter out certain frequencies which you may not want. Like the hiss, when you transfer music from like a tape or a record to straight digital, you're going to get some kind of a hiss. And you could filter that out, you know. And so it's all over the place. So it's an important thing. It's easy to see with tuning forks, but electronically, and in chapter, what did I say, chapter? In Physics 2054, you'll be tackling oscillating circuits, electrical circuits. And I'll be showing, if you're in my 2054 class next fall, I'll be showing you how to hack through that. It's not easy. It's a deluxe concept. All right. Let's do a buoyancy calculation. Can you imagine the nerves of these guys on the top of that shark cage? And look at that. What do you notice about that shark? Notice anything? This shark's been in a few fights. He's got some scar tissue, baby. He's got the gills. I mean, right here are the gills. Let me get my. These are the gills, right? But not this. That ain't, that's just somebody else, you know, somebody else trying to get to the shark cage before but he got there first. All right, let's do a calculation. What we're going to do is we're going to submerge a bucket of shrimp, a container of shrimp of 20 kilograms mass and of these dimensions, 2 feet down, and it's 3 meters high, so it'll extend down to 5 meters below the surface. So the upper shark is 2 meters down, is equals minus 2.00 meters, and the lower shark is at negative 5.00 meters. Now, sharks have got nothing to do with this, but I just felt like using the little shark figure that I found on my computer. All right, so those are the two different levels. Now, what we have to remember is the water pressure at the lower level, negative 5.00 meters, is going to be a little bit more intense, right? Because it's deeper. And the water pressure up at negative 2.00 meters is going to be a little bit easier, a little bit less pressure, right? Plus there's a weight force from this canister of shrimp. So we got a whole lot of forces to deal with. All right. Now the crate of shrimp, here are the specs. The upper and lower area, so we're assuming it's like a cylinder. And so I just, calculated 3.42 meters for the aspect ratio I wanted. Height 3.00 meters. And these are just numbers I made up so that we could have somewhat round numbers. And the mass 20 kilograms. All right, now are you ready to click? Because we're going to do some clicker questions now. All right, get your clickers out. Get your brains out. And be ready to cogitate. Question. The difference between using what and what? The question was, what is the difference between using H and Z? Well, Z is the traditional depth coordinate or the customary depth coordinate that we use. All right. If you're in 3 dimensions, you make the depth the Z coordinate. Now, H is just a symbol for, I mean, you could call the height of this canister anything you want. B or gamma in Greek letters, or any other letter you want. So that's, and it's oriented in the Z direction, but it doesn't have to be. That H could be, if you rotate that canister of shrimp, then it would be, in what, either X or Y or something between X and Y. All right. All right. So so this canister that we're looking at, here's a little kind of perspective view of it over here, this little baby. All right. So let's take a look at the first. Let me turn on my clicker here. Okay. And here's your first one. Calculate the density of the container of shrimp. And you have everything you need. And go ahead, kibitz and chat and counsel with your neighbor, if you have a neighbor. As soon as you came in late, it was right after I said, okay, everybody hush. And then the very next second you came walking in through the door. So I know it was just one of those crazy things. No, you weren't in trouble. It was just good comedic timing, that's all. So I haven't given you the radius or anything of the cylinder, but I have given you the bottom and top areas. So just assume it's a straight right angle cylinder. Okay, 30 seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, pretty good. Yeah, 1.94. Anybody here know the density of water? 1 gram per cubic centimeter. That's the same as 1,000 kilograms per cubic meter. So this canister of shrimp is 20 kilograms of shrimp. That's a lot of shrimp. But you know what else? It's a big canister. It's 3 meters. That's, you know, 9, 10 feet tall. So it's not a lot of, it's a big container for 20 kilograms of shrimp. Anyways, so the result is for this one that for sure this thing's going to float back up to the surface, okay? Because it's less dense than water. So there'll be a net upward force on it, and just like bubbles going to the surface, bubble is just air, a little sphere filled with air, and so that's what we've got here. All right, so here's my little canister deal. All right, now let's take a look at the free body diagram. Okay, first of all, go ahead and put a dot. And as always, we have the mass. Now, the mass of this thing is just mg. So that's 20 times 9.8. So what is that, 196? 20 times 9.8 would be, yeah, 196. Anybody verify me on that? 20 times, yeah, okay. So this one's going to be 196 newtons downward. Now, the canister has a top and a bottom. The top is going to be getting pressure from the water above it. The bottom is going to be getting pressure upwards from the water below it, because that water below it, if that canister weren't there, it would be supporting a whole column of water, plus the atmosphere above that. So we're not even factoring in the atmosphere. That's a whole nother atmosphere of pressure. All right, so we're just doing the water pressure here, or we're going to do the water pressure. All right, so you've got some pressure force downward, you got some pressure force upward. Now we know, and we've got the weight force, and we know that the net upward force is going to accelerate it upward, because it's going to float back to the surface. We already know that. It's not denser than water. It's less dense than water. Did you know that there's certain varieties of wood that are more dense than water? Lignum vitae. It's particularly dense wood. It'll sink. As soon as you cut it off the tree, put it in the water, and down she goes, down to Davy Jones' locker. One of the few trees, or one of the few species of wood that does that. Anyway, so we got the weight force, we got the two pressure forces. Let's put them in there. All right, so here's your pressure. I'll move the weight force over the side, and let me move my pressure force. Now this is the downward force applied to the top by the pressure of the agua. All right, so that's what my subscript, the force of pressure on the top, assuming it's a rigid container. So it's got to be light. It's got to be made of titanium or something like that. And I just dreamed these numbers up just so that have a nice, easy round numbers, but I'm pretty sure they're not very realistic. A 9-foot canister with 20 kilograms of something in it, and it's 2 meters down in the ocean. It can't be made of steel. A 9-foot thing made of steel, it's going to be way heavier than 20 kilograms. Anyways, so theoretically, that's the pressure. Now you've got some upward pressure, and make that one bigger. Now we're not going to calculate the pressure forces. We're just going to calculate pressures, but you can calculate the pressure forces later if you want. All right. And the sum of these three constituent vectors are going to yield a net upward force. So the red pressure from the top downwards and the weight force are going to be a little bit smaller, or maybe a lot smaller, than the upward pressure force from applied to the bottom of the canister. Now, why do I leave out the sides? The sides, if I wanted to, I could put left and right forces, and in reality, I'd have to think three-dimensionally. So all the azimuthal angles, as they go like a clock around the canister on a horizontal line at like at the midpoint of the canister, there's going to be forces. So if you etch in a line, a ring in the side of the canister, at the midpoint of the canister, you're going to get forces pressing in on that ring. And you etch in another ring above that, you're going to be getting pressure forces pressing in on that at that level. But all of those pressure forces will cancel, because at every level, at every angle, you'll have equal pressures facing each other. One from the left, one from the right. And then if you go 90 degrees, you got one from the front, one from the back. And if you go up, you got one from the, maybe a little bit less, but they balance up here. And they balance left and right. And they balance at 45. They balance at any degree you want to go around the horizontal clock on the etched into the side of the cylinder. So the bottom line there is, and you can make a note of it. When I was just interviewed for a survey, and the survey person, the interviewer, asked me, well, how do you uh, emphasize to students what an important concept is. And I told her, well, it's always like this. Let me repeat that. All right, and I just said it 2 seconds ago. Let me repeat. You do not have to factor in the side forces because the side pressure forces cancel. Every single, no matter which pair, no matter which side force you press in, you got one on the opposite side of the canister of exactly the same size. And it doesn't matter where you are on the sides. Now, top and bottom, you got problems. All right, top and bottom, you got a little bit pressing down from the top, and you got a lot pressing up. Oh, that means it's got a pressure differential. Yeah, and here's how you figure it out. I mean, here are the two formulas you use. The pressure is density times, and this is density of the fluid. So this is density of water, 1,000 kilograms per cubic meter. You better write that down because you got a clicker question here in about 2 seconds. You're going to be calculating a few pressures. So the pressure is density of the liquid or density of the fluid times G times Z. And this is in a static fluid. So if there's currents in the fluid or heat sources, it's maybe going to be a little different than that. But you're going to have rho GZ even if you have other stuff in there. Now the pressure force on the area of the canister or on any pixel of area is just whatever the pressure is times the area of that pixel. Now you can go top and bottom because everywhere on the top, the pressure, every square nanometer of the top gets the same amount of pressure. So the pressure up there is uniform. So all you have to do to figure out the forces there is, the pressure times whatever the area is. All right. Same thing on the bottom. Down on the bottom, every square centimeter, millimeter, nanometer, whatever you want to account with, it's going to have the same pressure force upward. If everything's level, if it starts to tilt and list side to side, then you got to do some trig. But if it's just sitting there floating in a cool, calm, collected state, horizontal top and bottom, then yeah, pressure force is just F times whatever or area times whatever the pressure is. Question.
If we were to experience a question like this on the final, would we expect it to be a calculation or would we expect
If we were to, the question was if we were to experience a question, see a question like this on the final, should we expect or should we assume that it's at rest and convenient? Yeah, I would give you some kind of either a direct statement or enough information to surmise, yes, that it would be. And just as a preview of coming attractions for the final, last time I taught a course at this level, I gave the students a question on the final about the pressure force on a dam. Like the Grand Coulee Dam or the, what's that one out by the Herbert Hoover Dam. Yeah, the Hoover Dam. Yeah, so you're definitely going to see some pressure stuff on the final. That's for sure. All right, so get those and make sure you write down the density of water, 1,000 kilograms per cubic meter, because we're going to try to calculate pascals now, and to get pascals you have to use kilograms per cubic meter, not grams per cubic centimeter. All right, here's your next question. Calculate the pressure of the water at z equals minus 2.00 meters. So forget about the air pressure above. We already know what that is anyways. But give me two Calculate carefully. Uh-oh. Uh-oh, spaghetti-o. I think I might have miscalculated here. Let me just double check this. Oh, hey, you guys were asking me about Wednesday. We had a calculation at the end of class, and it was off by a factor of 2. I had a typo in that, so I just removed it from the whole YouTube. So just X that out of your mind. And I did grade it. I deleted that question from, that was Wednesday. Yeah, so 2 meters down. I think I made it. No, this is good. I got it. Okay, what do we got here? Okay, 30 seconds to get your answers in. Starting right now. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh, yeah. Raise your hand if you got this. All right. Now, let me point something out to you. This is 2 meters down. All right. Now, ambient air pressure at sea level on a fair day is about 100,000 pascals. All right. So this is 19% of that. All right. So the full air pressure of one atmosphere, this is 2 meters down, so 19.6% of one atmosphere. You got to go 10 meters down approximately, and then you'll be at water pressure of about 100,000 pascals. But just 2 meters, it's noticeable. And you know what? Is anybody in here a scuba diver? Have you were you trained to even be careful in like a swimming pool for getting bends? Yeah, because I heard that if you go in, you can even get bends in a swimming pool if you're not careful. What's that? Yeah, 5 feet of water. Yeah, so you got because you're breathing pressurized air, so it's a whole different. It's like being an astronaut. All right, next question. 5 meters, please. Is this getting boring yet? It looks like it. I see people, just looking around and stuff. That's good. If it's boring, that means you got it, right? You've learned something. Yes. I got you right where I want you. Okay, 15 seconds, starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go. All right. 3 of you haven't voted. Too late. Yeah, 49,000. And now let me just reinforce, or should I say, let me repeat. Compare this to atmospheric pressure on a fair day, about 100,000 pascals. This is 49% approximately. All right. And it's 5 meters down. So that's why we say, about 10 meters down, you've added a whole atmosphere of additional pressure. And you got all the atmosphere from the edge of space all the way down to sea level. That's one atmosphere. And then about 10 meters down in the ocean, in the briny deep, another atmosphere, another 100,000 or so, depending, on the conditions. But usually it's about 10 meters. Now, second thing I want to emphasize to you, and this is actually going to be applied when we get to the Bernoulli equation on Wednesday. There's a pressure differential upward. How big is it? 29,400 pascals. All right. And if you think about it, think about how big an airplane wing is. All right. An airplane wing, I was just reading about 747, and they got this big version. They just launched or flew for the first time this big scaled composite plane with a huge wingspan and 2 fuselages that can launch rockets into space from high altitudes. Put small satellites up, and it's got the biggest wingspan ever. And so I was looking at other big aircraft. The 747. 8, I think it's called, is like 250 feet long. It's enormous. They have enormous wings. Every square meter of a wing, if it had that much pressure differential, that would be 29,400 newtons upward. For every patch of wing about this big, square meter, you're getting 29,400 newtons upward. And just think how big an airplane wing is. I mean, you could have a dance on the wing of one of those babies. They're pretty big. Now, we're going to dismiss, but if you want to ask questions about homework X, you can come on up to the front. Otherwise, I'll see you Wednesday.